Hey guys, welcome back. So today marks the start of a new chapter in our math journey, and that is the start of calculus. So specifically, we're going to be focusing on the first half of calculus, and in the next playlist, we'll be going into the second half of introductory calculus. So, what is calculus, right? Why study calculus? Let's go with the big picture. In the grand scheme of things, calculus is how things move, right? It's the mathematics of change. And what does that mean, right? You can say, for example, you have a bow and arrow here, and you're shooting an arrow to a target like 15 feet away. What you're going to say, okay, well, I pull back on this arrow, and then I let go, and then it goes this way, and, it's going to fly and hit this stuff. And you'd be right. But there's specific equations and there's specific models that you can use to predict and kind of outline how things move for any shape, for any object moving anywhere. And I guess, at the very core of it is calculus. Calculus is the building block of so many different subjects like physics, and then you have particle motion, you have a lot of different Newtonian mechanics, and it just keeps branching out into different stems and fields of physics. And at the core of it all is calculus. So it's going to stem out, stem out, stem out, and it just goes into all kinds of different places. And I guess if you want to think about it a little bit more intuitively, honestly, no matter what subject you look at, mathematics will be the foundation. From there, you can build up to physics. From there, you can build up to chemistry and biology. And you can just keep stacking the tower as high as it goes to see where you get. So, I guess while comparing this to algebra, although algebra helps us solve for unknowns, for something that looks like this, we can plot this out, we can find the roots of it, or we can, use the quadratic formula, stuff like that. Algebra helps us explore unknowns, and geometry helps us explore shapes. Calculus calculus asks questions like how fast is something changing at this very second? Or it can say, how do you predict the total amount of something as, time goes on? Say for example, we have a cup here, and there's a leaky faucet that's just dripping water into this. And we know that it drops maybe 20 drops. This is going to be a very bad, unit of measurement, but just for the sake of this introduction, let's say there's 20 drops per hour. We can find out based on how radially big this container is and how high it is, and for the formula of a cylinder being pi r squared times the height, we can find out all of these things and use this to see that after maybe 30 minutes, how much is this jar going to be full? Is it going to be up to here? Is it going to be up to here? We don't know. But that's something that we can do with calculus. So, at its core, calculus is about two very fundamental ideas. The first one is going to be derivatives. Derivatives. And the second one is going to be integrals. Integrals. So, what do these two words mean? Why do they matter? And how are they going to be defining calculus for us? Well, derivatives is essentially the first half of the course, and integrals is the second half of the course. However, integrals don't really get the due weightage that they deserve, because even though integrals are covered in the second half of the course, primarily in Calculus BC, there is a lot more to do with integrals, in my opinion, than there is for derivatives. And you'll see why once we get there. But, for the definition wise, a derivative is measuring the instantaneous rate of change, instant rate of change for something. And what does that mean? Well, say for example, there was a car and it was going, it was going 10 miles per hour here. And then once it gets to here, it's at 5 miles per hour, 5 miles per hour. And then it speeds up again. Maybe now it's at 20 miles per hour. Well, it's going, different speeds at all different times. But the derivative, if there is a function plotting how fast this car is going with respect to time, the derivative would tell us, how fast it's going at a specific time. Sorry, if we were to put position, x being the position, and if we were to plot it against time, and the car may be doing something like that, the derivative of this function would tell us how fast this car is going at any given time. So that is the purpose of a derivative. An integral is the exact opposite, or at least not fundamentally at the very beginning, but once you kind of realize how a derivative is calculated, you'll see an integral is mathematically opposite. And that is that it measures accumulation. It measures how much something is accumulated over time. So if I were to convert this same analogy here, right, and if I were to plot, the car's speed versus time, right, and say it looks something like that. It doesn't have to be perfect, right? And then say I wanted to find out how much the car moved from time is equal to 3 seconds to time is equal to 6 seconds. The integral of this function from 3 to 6 will give us this area right here, the area under the curve. And that will tell us how much the distance has become. So don't worry too much about, the car speed and this graph right here and this graph right here. All those things will be touched up on. But I just wanted to kind of tell you what the two overarching aspects are. It'll be a derivative and it'll be an integral. So just keep those in the back of your mind for now. So why study calculus? Why do it, right? Well, there's three, I would say, big picture things you can do with this, but calculus is such a versatile tool to have in your toolbox that you could use it for a lot of things. But the first thing that I can do is predict the future. And what do I mean by predict the future? We can say about how populations might grow, how investments might change. Basically, given the current behavior of a function, say if it's going something like this and it starts going up, we can say that after this point, it must keep going up, and there's formulas for that. So that's the first one. The second one is to optimize a scenario. And what do I mean by optimize a scenario? Well, in any given situation, right, there could be a finite amount of resources, but you're trying to maximize the output that you got. So, in other words, you're trying to maximize the output and minimize the input. In essence, trying to do the most amount of work with the least amount of effort, in some sense. And then the third thing is, I guess, understanding random phenomenon, random patterns. And what do I mean by this? Well, another thing that this kind of just ties into the future prediction scenario, but if I were to have a chemical reaction that doesn't move super nicely and stuff like that, I can kind of construct a function to exhibit the behavior of that chemical reaction. So say for example, I had a population here and that was growing at some random rate. It wasn't constant. It may not be geometric necessarily, but it's not going to be constant. Well, I can see how much I have at time is equal to 0 and then 1 and then 2 all the way up until like 15, for example. And, this will give me some number, this will give me some number, and all of these will give me some number. So based off the input that I have and the output that I have, I can kind of daisy chain together a kind of function, and that will help me predict this, generally speaking. I'm going to put one of this, generally speaking. So what kind of things can you expect with derivatives for this first course? Well, let's kind of dive into it. The first thing is a limit. And this is kind of, in its name kind of thing. This is just saying as you are approaching something, in this case, it'll be a point on a graph. If I have the function y is equal to x right here, it's a very sloppy line, but if I were to, say approach the point x equals 5, on this function, say I'm, a hiker and I'm going up this graph up till this point. I want to see what where do I, what height do I get to? What is my y value as I approach an x value? So that's what a limit is. As you approach an x value on a graph, what is the corresponding y value? The second one is the introduction of a derivative. So I'm just going to put introduction of a derivative. So before we kind of hop into using derivatives, we have to understand what a derivative is first. We have to understand the nature of it, the intuition of it, stuff like that. But once we use, the building blocks, then we can dive into applications. Applications of derivatives. Oh, very messy handwriting there. Just ignore that. But yeah, we can dive into applications of derivatives, and there will be some, aspects of analytical interpretation of derivatives. So basically what this means is once we understand what a derivative is, we're going to have to apply it in either a formula way, or we're going to have to kind of use our knowledge of derivatives and how they operate, and we're going to have to solve a problem that's a little bit harder to model mathematically. Then the final thing, or the next thing that we're going to tap into is integration. We're going to define what it is, we're going to define how to use it, and use it in the scope of this course before getting into more advanced integration techniques that are kind of primarily focused on in Calc BC. From there, we dive into a topic called differential equations, which seems daunting at first, I would say, to everybody, just because of the name in itself. Differential equations, like, why is the equation different? But once you get to realize that it's just, a product of derivatives and integrals, it's like a combination of both of them, then you'll see that it's just using the tools that you already know and then kind of going from there. And then the last thing is applications of integrals. Applications of integrals and differential equations, which, this kind of ties back up into this because we're using integrals in this. But you have applications of integrals. Excuse me. And that is essentially the scope of this course. So for a derivative, it'll be something like this. For a graph, like this, and we pick a point here, right? Say, for example, this is x is equal to 3, if this was y and this was x. Well, what we want to know is, well, we have a limit here, right? And every graph has a slope, This one happens to be a very uniform slope of 1, because this is just y is equal to 1x plus 0, where 1 is our slope. This is an upside down quadratic, something along the lines of y is equal to negative x plus 3 squared. Excuse me. And, there will be some shift. We'll just say plus like 7. So it's shifted up as well. So because of that, there's not exactly the same slope everywhere on this graph. Right here, there's a slope. Oh, let me draw that a little bit nicer. Right here, there's a steep slope. And then right here, there's a less steep slope. And then right here, there's an even less steep slope. Here, the slope is 0. And then it becomes a little steep again, more steep. But you get the basic idea. So what we're trying to do with derivatives is use the concept of a limit and say that as we approach a point, so we're approaching 3 here, what does the slope do? How does the slope change from more steep to less steep to essentially being 0 at this point, right? So we want to see what the slope of a function is at any given point. So we're going to combine limits and properties of limits and our, understanding of slopes to try to model this. Now the same thing in reverse, as I kind of talked about before with integration, where if you have a function like this, and say it's something like that, and we want to find the area under this curve from here to here, we're going to use our understanding of limits as well as our understanding of graphs to try to see how can we find the area under this curve. And then for our final, I would say, new topic, concept of differential equations is honestly just reading slope fields. And what is a slope field? It's a derivative. So you're kind of combining derivatives and integrals here because, they might give you something that looks like this, where you have a bunch of slopes, and then, it gets steeper and steeper, and then something like that. And then as you go, this is to this way. Maybe if you go this way, the slope field will become leaning towards this side, right? And then, if you go down, it might, right? And all these things goes to show that I'm just drawing lines here, but the intuition here is that if I were to pick, a function, it would look something like this, where the slope at this point, they're all kind of pointed down, and the slope over here is pointed up. So using that and our understanding of derivatives, once we build them up, we'll be able to take the function that is, dry fit, this isn't a great fit, but we'll take this function and integrate it because it'll be the opposite of a derivative. And then we can get our base function, which is f of x. So all of this, is just a very high level overview into what happens in the scope of calculus and the scope of calculus AB. But I just wanted to go and show you that this course, although it may seem a little, obscure at first, maybe it just seems like there's a lot of random topics. Once you learn about the applications and the fundamentals of this course, there's nothing that you can't do. So I can't wait to see you in the next video, and let's dive right into our topics.